Okay, let's start. Good morning. So I've graded problem set 1, me and the grader. I'm generally happy about the outcome. I think tomorrow I'd like to say a couple more words about sort of the your feedback coming from the Google form. But for now, let me just say that if you look at your work on Gradescope, probably your, so there's not going to be very explicit feedback, but so it's typically, it's like even if, so even for the problem that was graded for accuracy, which was the last problem, I just typically say part A is incomplete or something like that. But because I thought it would be better to have sort of like a solution, let's say, and if you go to Canvas, under the Pages tab, there's a page for selected solutions, and I uploaded solutions for problem set for problem 4. So you can have a look at that and sort of compare and contrast how you did and stuff like that. And if things are still not clear, then we can discuss further. Yeah, so I'm hoping to keep updating this document for selected solutions. Probably each week I'm going to add one more problem, which is going to be probably the problem that was graded for accuracy. And we're going to sort of like populate that document as time goes by. It's going to be a nice document. Okay. Are there any questions? Okay. So this week is really all about sequences. From calculus classes, probably you're familiar rather, with this idea of having infinite sums. Sequences are somewhat related. So instead of looking at the sum term, the whole infinite sum, you look at the terms as sort of like a discrete time signal, if you want. So we're going to sort of study that a little bit. And it turns out that it is good for, so sequences are useful for modeling purposes. It sort of like models, for instance, measurements that you take in discrete time steps, but also, perhaps not that surprisingly, they are very foundational objects, and you can do a lot of things using sequences. In particular, you can sort of like talk about continuity of functions in terms of sequences and stuff like that. And so we're going to start talking about that. Before that, though, I wanted to talk a little bit more about these ideas, these notions, sup and inf, because in problem set 2, you're going to have to deal with these ideas, these notions, and I would like to prove some claims about how these guys operate, and then if you have time, we can start talking about sequences and subsequences and other things. So, supremum we had defined last week on Friday. So it's a function that takes as inputs subsets of the reals, and as outputs gives you an extended real number, possibly minus infinity or positive infinity. And it is defined like this. If A is nonempty, if A is empty, it gives you minus infinity. If A is not empty and bounded from above, by the completeness axiom, we know that there's a least upper bound as a real number. So the supremum of A is going to be that real number. And the final option is A is non-empty but is not bounded from above. In that case, you have infinity. So the way I like to imagine it is like this. So I have here the real line. And let's say somewhere here in the middle is my set A. It's a bunch of points. It could be an interval. It could be sort of something like a fractal, like a Cantor set or whatever. Something, okay? And I'm imagining the sup to be sort of like the upper clamp. So I'm trying to upper bound this A. If A is unbounded, in other words, if you have a bunch of like points in A that goes to infinity, well, you cannot sort of clamp it any further. So you have to be at infinity. But if it is bounded, that means that you can sort of like pull it back all the way to here and so on. Okay? And then sup of A is the best clamp. It's the optimal upper bound. Okay, that's how I think about it. And of course, I hope this also makes sense that if A is empty, then if I'm trying to upper bound it, well, I'm sort of like trying to push it and push it and push it, but there's nothing stopping me. So I'm just like, keep going to negative infinity. Okay, that's the idea. And then max is very similar. It's pretty much the same thing when you think about it, except that max of a subset is not defined for arbitrary subsets. It is undefined if, unless this condition holds, namely that sup of A has to exist as a number, and it has to be included in A. Okay, in which case max of A equals sup of A, otherwise it is not defined. Okay, infimum is the same idea, but instead of trying to bound things from above, it's the other side of the clamp. Okay, so if A is unbounded from below, that means that you have to be at negative infinity. Well, if it is empty, it's going to go all the way to positive infinity. There's nothing stopping you. If it is non-empty and bounded from below, you're going to start here, and you're going to sort of like try to optimize the lower bound, and that gives you the optimal lower bound is the inf. So you see, this interval, inf of A comma sup of A, is sort of like the best interval that you can sort of use to model A, if you want. A could be something crazy, but ultimately, the closed interval from inf of A to sup of A is the best interval that approximates A, in a sense. Okay? Yes?
So for an empty set, the inf and sub are swapped, but why not just say that it's undefined? Is there something that we could do with the empty set in their inf?
I mean, yeah, so you can say that if A is not empty, if A is empty, then inf and sup are not defined, but I can define it in a consistent manner. So, yeah, I mean, so ultimately, I would like to, yeah, so this is sort of like a matter of taste, really. In the textbook, I think they just say it's not undefined. But this makes perfect sense, and in a sense, you have some continuity as well, right? Because you can say, what is the, let's say, inf of, well, x to infinity. Of course, this is x. This is the least bound, right? And as I take x to negative infinity, this too goes to negative infinity. What am I saying? Oh, I should be doing the other way around. If x goes to positive infinity, so that this set gets closer and closer to the empty set in a sense, right? So as x increases, you're taking smaller and smaller sets, while the inf goes to infinity, right? Am I correct? Yeah, exactly. So you can say if x goes to infinity, this interval goes to empty set, and inf of it goes to this value that I defined here. Does this make sense?
Yeah.
Yeah. So somehow I would like to imagine that these are really continuous functions also. It's a matter of taste. There's a similar thing going on, for instance, when you look at limits. Sometimes you look at the limit of a function, and then the limit is infinity. It's like, so for instance, if you were to look at this, well, you can say this is undefined, or you can say it is infinity. Right? So it's undefined in this sense. It grows unboundedly. So they are both the same thing. Yeah. So it's a matter of matter of taste whether or not something is defined really. Okay, any other questions? How about functions? There's a big problem in problem set 2 about these ideas applied to functions. Well, in the case of a function, when you're looking at the inf or sup or the min or max of a function, you just look at the image of it. That's a subset, and there we can define it. So let me do this. For f, a function on some set x, taking values in the reals, a function max, min, sup, inf are, well, of f, are defined as those of its image. So for instance, you can see sup of f. It should be always defined. And so this is just sup of the image of f. Image of f is a subset of the real, so I can apply the notion of a sup on it. You can also see these notions, these notations. So sup of f of x such that x is in x. Or people like to abbreviate it like this. Sup of f of x where x, lowercase x, varies in uppercase x. So you take f of x for some arbitrary lowercase x and then you optimize it. You get the best, you get the highest one. And similar notations hold for min and inf and all that stuff. Okay. Now in problem set 2, there's going to be a problem about, oh, you know, what is the sup of f plus g or something like that. And there's a bunch of formulas. You're going to have to sort of manipulate these things many times. And this is sort of like the way to get used to them. Any questions? Okay, let's prove some statements about these things. Okay. Yeah, let's start like this. So this is sort of like parts of a theorem in the textbook. Look, let's just write them as claims. For any subset, well, inf of A is less than or equal to the sup of A. Okay. Of course, I should be careful, just like your colleague suggested in a second ago. Well, if A is empty, there's nothing stopping me here, right, for the lower bound. So this is going to be positive infinity. This is going to be negative infinity. So that cannot hold, which means that I need to assume that here A is empty, right? So let's say here implies. Now that's a claim. proof? Well, I'm just going to use the definitions. Okay. So what do I have? I have that A is a subset of the reals and A is nonempty. That's pretty much all I have. And I know the definitions of inf and sup. Well, I can just take a point in A. Then by definition, I know that inf of A, because it's a lower bound for A, it has to be less than or equal to this guy. And likewise, sup of A, because it is an upper bound, it has to be greater than or equal to it. So then, by definition, okay, and of course, less than or equal to relation is transitive. In other words, if this guy is less than or equal to this, and this is less than or equal to this, then this is less than or equal to this, which is what was claimed. Okay, that's a proof. Now, in this proof, for instance, I actually don't use anything about whether or not A is bounded from above, below, whatever. Right? So these guys could be positive or minus infinity. That doesn't matter. Questions about this? Okay, so the best lower bound is dominated by the best upper bound. Okay. Here's another claim. Yeah. For any two subsets of the reals, if A is a subset of B, then I have certain inequalities relating the inf and sup of A to the inf and sup of B. Maybe this is a very nice idea, so maybe I should try to draw a picture. So here's my real line. So what do I want? I want something like this. I want to relate inf of A to the inf of B and sup of A to the sup of B. Any guesses as to what sign, what symbol should I should put here?
Less than or equal to?
This one?
Maybe greater than or equal to.
This one?
Yeah.
Okay. How about this one?
No.
Other way around. Yeah. Of course, your colleague is correct. So what is the idea? Well, I have here, I mean, you can test it out with intervals if you want it, but I have here a subset A, and then somewhere here is a subset B. Okay, A is a subset of B. Okay, sup is the upper clamp, right, upper bound. So as I'm pushing it from positive infinity, first I'm going to hit, I have to hit first B. Maybe this is sort of like flush this way, but certainly I cannot be hitting A before I hit B. Okay, I'm going to be clamping B before I clamp A. B is larger. And the same idea holds for the infimum. Okay, so I'm going to first clamp B and then clamp A. Does this make sense? Okay, so that's the claim. This is the intuition. The point is to turn this into a proof, this intuition into a proof. Okay. So we need to now separate cases. Either B is empty or it is not. Right? There are no other options. So there, B is empty, XOR, exclusive OR, B is not empty. If B is empty, since A is a subset of B, A has to be also empty. In this case, I don't know. A could be empty or not. But you see, in this case, both A and B are the same set, which means that their infs and subs are going to be the same number. Okay? So in this case, inf of A equals inf of B equals, so what was it going to be? So it's the best lower bound, so it's going to be positive infinity. And certainly if two things are the same, one of them is less than or equal to the other one. It's a silly thing to say, but it is true. And likewise for the subs. So in this case, minus infinity. Okay, does this make sense? So I have sort of like a decision tree. I'm saying either B is empty or it's not. If B is empty, now I have a further assumption. So some people would call this a case by, or a proof by case analysis. If B is empty, then A is empty, and then I have this thing. You could also say if B is empty, there's nothing to do, or something like that. It's obvious, whatever. And really, when you're in this situation, things are getting different. You need to do some work. Yeah, let's see. In this case, I can again split it into two cases. Either A is empty, or it's not empty. Because empty set is a subset of any other set, after all. Let me enumerate these. Let's call this case number 1. Let's call this case number 2. In case number 1, I should also mention that probably you don't need to do this case analysis and stuff like that, but that's kind of my style. I like sort of separating cases and sort of like handling them one by one. I'm sort of like factorizing what I have to do and just dealing with every single case. In case number 1, A is empty, B is not empty. Okay? Because A is empty, I have that inf of A is positive infinity. Sup of A is negative infinity. Oh, okay, that's fine. But then, I don't care what really B is. I wanted to do this. Inf of B is going to be at most infinity, and sup of B is going to be at least minus infinity. So again, really, there's nothing to do. Oh, sup. So that's that case. The second case is the case where you actually have to do something. So now I have that both A and B are non-empty. So I cannot do this logical shenanigans. I have to do something. Well, if A is non-empty, I can take a point in A, lowercase a, let's say. But A is a subset of B. And by definition, sup of B is supposed to be an upper bound for any element in B. Okay. So, thus, sup of B is an upper bound for A. Any element of A is bounded from above by sup of B. But then by definition of sup of A is supposed to be the best upper bound, which means that it cannot be greater. And that's the end of the proof. So we're going to keep playing this game over and over in this class. You have a bunch of things, a bunch of quantities, maybe sets, whatever. And you're going to sort of minimize and maximize this and that quantity and so on. And then that's going to give you some inequality ultimately. Okay. Now it's going to matter in which order you sort of optimize things. Okay. Any questions about this? Okay. So good. Let me do, let's see. I'm going to start sequences, but I think it's going to be good to do at least one more. Okay. Let's do this one. Well, before that, maybe I should give you, as an exercise, the next piece. And this is really sort of like a foundational exercise. Let's take a non-empty subset of the reals and look at minus a. Minus a is going to stand for, well, it's the reflection of a through the origin. Define minus a to be minus lowercase a, which is a real number where a comes from uppercase a. Okay, this is 0. Here's your subset a, sort of like reflected to that side. And this, so you see, switching between a and minus a really gives you sort of the duality between sup and inf. And this exercise is really about that. I want to relate sup of a, well, to the inf of minus a, right? Because if I have here a, well, then an upper bound for it, when I reflect it, right, when I flip the whole real line, is going to turn into a lower bound. So somehow, sup of a, it seems like, equals minus inf of minus a. And indeed, that is true. So maybe I should write it like this. Sup of a, and then I want to relate it to inf of minus a. I'm saying this is this. Okay. How are you going to prove it? Well, you're going to say this is less than or equal to this, and vice versa. You're going to prove two things. And how do you start? Well, all you know is that A is non-empty. You have to use that. You're going to take a point, and then you're going to optimize, basically. Questions? This is proved in the textbook as well, so if you're having trouble, you can have a look at it there. You can have a look at the textbook as well. Okay, so here's a more complicated version of this, but it is instructive, so I want to prove it. Now I should also perhaps make a statement about, or make a comment about the names of these things, right? So in the textbook, all of these parts are really parts of one big theorem, and I'm just calling them claims, okay? And you're going to see in the textbook there's a bunch of theorems, but not all of them are proved. Some of them are put in the exercises. So is it a theorem? Is it an exercise? Well, in a sense, that's why I like to use the word claim. It's somewhat more neutral. Theorem is supposed to be something large, something big, something like the fundamental theorem of calculus or some fundamental theorem of arithmetic. Even though these ideas are useful, of course, I don't think necessarily that they are sort of magnanimous, let's say, magnanimous enough or bombastic enough to be called a theorem. So I just reserve that word. Okay. So let's look at this. If if I take any two subsets, yeah, let's just take them to be non-empty for simplicity. Because as you saw, if I don't assume that these sets are non-empty, then I have to do some case analysis, blah, blah, blah. Let's just not worry about that. Let's say that neither of them is the empty set. And while we're at it, you see, the relation of not being equal to is not a transitive relation. So just because this is not equal to this and this is not equal to this, I'm not really saying that this is also not equal to that. They could be equal, after all. Define A plus B. And similar to this, over here, I'm just going to define it to be the sum of elements in A and B. This is what is called the Minkowski sum of two sets. These operations are very useful in sort of computer vision and other things, because you really want to think of sets as shapes, and you sort of do certain manipulations and so on. Mathematically, they're also very interesting, of course. A plus B in R. You see, I'm using the set builder notation. That's the general shape of an element here, such that lowercase a comes from uppercase A and lowercase b comes from uppercase b. Well, I want to relate the sup of this guy to the sums of the sups. It turns out that they're equal. That's the claim. How to prove it? Well, first I'm going to try to show that this guy is bounded from above, let's say, by this, and then this guy is bounded from above by this. Proof? Typically, when you have things like this, one side is rather straightforward, and then the other side you need to do something, okay? So I know that neither of these is empty, which means that A plus B2 is non-empty. Let X be an element in A plus B. Then for some A in A and for some B in B, X equals A plus B. Now, this lowercase a and lowercase b are not unique, okay? There might be multiple elements that add up to x, okay? But at least there is one a and there's one b. Well, a is bounded by sup of a and b is bounded by sup of b. Well, if I were to add them up, that's going to give me an upper bound for this guy. So for any element in A plus B, sup of A plus sup of B is an upper bound. Okay. Really, if I want to be more careful, I should sort of like split cases. I should say, either both of them are unbounded, in which case this is positive infinity, blah blah blah, or they're both bounded from above, in which case this is a positive number, and so on. So you can sort of like keep going like this, but it's clear what I'm trying to do here. In any event, any point in A plus B is bounded by this guy, while certainly the sup of this has to be bounded by this also. Because sup of A plus B is the best upper bound. Okay. So this gives you this side. Now I want to show the other way around. And so what you can do here is that because you're sort of splitting the statement into two parts, you can sort of put somewhere in your proof some symbol that sort of signifies it. So what you can do is, because this part is really about this inequality, you can put something like this here. That would signify that, oh, I'm trying to prove this side first. Okay, this side is correct. Okay. Now we need the other side. And this is going to be a little bit more complicated. I hope I'll be able to figure it out. I was trying to prepare this before, but I got confused. So. Okay. Well, we'll figure it out together. Let's say it's not correct, okay? For a contradiction. Well, sup of A plus B is strictly less than sup of A plus sup of B. By one of the four properties of numbers, I know that I can inject some number in between them. Okay? In fact, it could be a rational number if I want it. It's not going to matter that it's a rational number really for this. Then there is an M real such that this happens. I injected this M in between these two numbers. Okay. How to continue? Well, I want to do something about, so I want to zero in on these two guys. Well, I could try, yeah, question.
Is it not possible for those to be less than or equal to sign? Couldn't they all be equal to each other?
Well, the density statement was that there's a number between, strictly between, right? So because I assume this, the difference between these two is a positive number. And then the density assumption for the rationals says that there's a number between that number and 0. Yes. Good point. Any other questions? Well, I want to do something about this sup of A. Divide and conquer, okay? So I can try sending this guy to the other side, but if B is unbounded, then things sort of get complicated. You should be always careful about positive infinity and negative infinity and doing inequalities with them. Even though I define them, if possible, you should always work with numbers, or at the very least split the cases. So let's split the cases. Either B is bounded from above or not. In other words, either sup of B is positive infinity, XOR, exclusive OR, sup of B is a finite number. It's not an extended number. In this case, so B is bounded, B is unbounded. If B is unbounded, because A is non-empty, A plus B too is unbounded, in which case both of these, both this and this thing, is going to be it's going to be infinity. A plus B. Because one of this is positive infinity. And A is non-empty, which means that sup is not minus infinity. So this is a finite number or positive infinity. And a number plus positive infinity, infinity, and infinity plus infinity is also infinity. In any event, there is nothing to do here. So this branch is done. We need to figure out what to do with this branch. In this branch, well, I can send this. Now it's an honest to heavens number, okay? So I can just do arithmetic with it. Sending it to the other side, I have this. M minus sup of b, it's a number, is a number strictly less than sup of a. But sup of a was the best upper bound. Because this guy is strictly less, that means that this guy cannot be an upper bound. In other words, there is some number in a in between these two. Let's call it a star, such that you can inject it. Okay. Now, as opposed to the previous situation here, now I have to put less than or equal to here, because a, maybe uppercase A contains only one element. I don't know, right? Could be sup of a could be equal to this guy. Certainly a star cannot be larger. What is important is that this guy is strictly greater than this. Okay. So now I need to do something about this other guy. So you see, I was able to reduce or unfold sup of a, and I was able to get some actual element in my set that does things. Okay, it's a number now that is in A. Now I want to do something similar, and I want to convert sup of b to something that I can manipulate much easier. Yeah, what I can do is the following. I can send this sup of b to this side to get, and a star to this side actually. M minus a star is like this. Okay, I just replaced this with this and this with that. Well, by the same reasoning, there is some b star that is strictly greater than this. Okay, we're almost done with the proof, I think. We have about 5 minutes. Okay. We're done actually. Do you see mate in one step? Or 2 steps perhaps. I have an A star and I have a B star. These are truly elements in A and B. Sup of A possibly is not in A, and sup of B is possibly not in B. What to do? M is dominated strictly by A star plus B star, which is an element in A plus B. Okay. It's a contradiction. M is not an upper bound for A plus B at all, right? I'm glad I was able to figure it out. Contradiction. If you want, you could also say this. A star plus B star is dominated by sup of A plus B. Maybe I should write it like that. Let me write it here. So M is strictly less than A star plus B star, which is an element of A plus B, which means that sup of A plus B should be dominating this. But then m is strictly greater than this further. So you see the contradiction is I have a number m that is strictly greater than itself. I can do this lightning symbolism for a contradiction. Does this make sense? It's a silly game, okay? That's how it works. That's how you do math. Okay. Now there's a version of this with inf and blah, blah, blah. And instead of a plus here, you can put a minus, in which case you need to be using sup and inf together. These are in the textbook. I don't want to spend more time on this. Now it's your job to do as many sort of manipulations as possible with things like this. Let me introduce the notion of a sequence in the remaining 2 minutes, and then we'll be done. A sequence is, well, it's just a function whose domain is a certain subset, or whose domain is integers. Let's put it that way. Let X be a set. So definition. A sequence in X is a function. Let's use this notation, lowercase x with a subscript bullet. I'm going to say a couple more words tomorrow about this notation. Going from, let's say, non-negative integers to X itself. Okay. Now, you see a bunch of different notations for this. Maybe I should mention that and we'll be done with this. So I'm going to be typically using this thing. So this bullet signifies, oh, that's a placeholder. So I'm going to say x sub n is the value of the sequence x bullet at time n. Okay. Other notations for this is something like this, or this, or this, or this, or this. This is in signal processing, or this, and from 0 to infinity, dot, dot, dot. There are millions of notations for the same idea. Okay, I'm going to use this notation. Okay. I think that's a good place to stop. We'll continue tomorrow. Thank you. Okay, let's start. Good morning. So today we're going to work on sequences. We're going to talk about a new type of mathematical object, which is called a metric space. And then we're going to start looking into ideas about convergence. And then on Friday, we're going to keep working on these things, and then we're going to start proving certain things. And really after this week, things start to open up. Okay, so, oh, by the way, I'm taking attendance. There's an attendance sheet going on, so please make sure that you sign it. Okay, now instead of focusing on sequences of real numbers, I'd like to discuss sequences in abstract, because we're going to need to talk about things like sequences of functions and other things, even for this class. And so I think it's easier to just get used to this idea of a sequence in the abstract and then sort of specialize, instead of first focusing on sequences of numbers and then freaking out once you see sequences of functions or other things. Okay, I take a set x. A sequence is nothing but a function indexed, or whose input values are integers, positive integers, or rather non-negative integers. Okay, and so the way I'm going to write it is I'm going to write x sub bullet. This is the bullet sign, let's say, it tells you this is where I put the input if I try to evaluate. And I'm going to try to say, I'm going to call n here the input time, right? This is going to be my time parameter. I'd like to imagine it like this. And x sub n is going to be the value or the place of the sequence x sub bullet at time n. So time, and this is where x sub bullet is at time n. Okay. And typically, instead of sort of writing a function like this, I'm just going to write x sub bullet element in x. You see, earlier we talked about how this is the notation for, oh, this thing is an element of this, but now I'm starting to do a what is called an abuse of notation. So this is an abuse of notation. Also, sometimes instead of starting the index at 0, you might start it at 5, whatever, or -7. So typically, that where you start the indexing changes from time to time. If you want, you can take all integers too. For instance, in signal processing, that's something that you do. It's just more convenient to think of sort of like a bi-infinite sequence. But for our purposes, this is going to be the typical example. Now, I'd like to give, or this is going to be the typical form. I'd like to give some examples. So, of course, we're going to spend a lot of time on sequences of numbers. Sequences, let's say. So, for instance, I can think of, let's say I'm starting at 1. Well, x sub n, let's say, equals 1 over n. This is one way of defining a sequence. Okay, so 1, 1 over 2, 1 over 3, and so on. It goes on. Another example, for instance, yeah, I can define something like this. So this is one example. Another example, perhaps an integer sequence. For instance, the so-called Fibonacci sequence is an example. So I can say x1, x0, let's say, is 1, x1 is 1, and then the rule is that to get the next term, you add the previous two, right? So, and then 3, and then 5, and so on. So xn plus 2 equals xn plus 1 plus x sub n. So this is what is called the Fibonacci sequence. Okay. Now, really underneath this, so this is what is called the difference equation, or recurrence relation too. That's also a word that you would see. The fact that looking at this, I have a well-defined sequence really uses the principle of mathematical induction underneath. Okay? Of course, it's not that important, but you should think of it like that. Because ultimately, this tells you a relation between different terms. And then to figure out x sub, oh, thank you. Did everyone sign the attendance sheet? So in principle, or in actuality, to figure out the 10,000th Fibonacci sequence, you would need to sort of run a certain algorithm. And so the length of that algorithm would be unbounded in general. Because for arbitrary n, you would typically need to go further. But even if that is the case, principle of mathematical induction says that that's not a problem. It's still a well-defined mathematical object. Okay. Now, of course, if you know some linear algebra and stuff like that, you can figure out a closed formula for the nth term of the Fibonacci sequence. But let's not talk about that for now. Another sequence, of course, could be something like a random thing. So for instance, I can imagine x sub n to be, well, the number of students attending the class, this class, at day n. Number of students. Nth class. Now, this too is a well-defined sequence, okay? But not, so you cannot really justify why this is well-defined based on what we discussed so far, because in a sense, the semester didn't end, so we're sort of in the middle of it. So we don't know, like x sub 100 or whatever. Probably we're not going to have 100 classes, but anyway. X sub 50. We don't know what value it is exactly, but you can imagine it to be something like a random sequence. And so to really formalize this idea, you need sort of like a background on probability and stuff like that, and we're not going to really spend time on this. But certainly for modeling purposes and so on, stochastic processes really allow you to think about these kind of things. Okay, so there are many sort of sources of sequences, and we're going to keep working on these throughout the class. Now, any questions so far? So here's a sequence of functions. This too is going to be very important for us. So for instance, because now my sequence is going to be a sequence of functions, instead of using x, I'm going to use a more evocative notation, and I'm going to call it f sub bullet. Well, let's start with 0. And my output is going to be, let's say, the set of functions from the unit interval, taking real values. Recall that this was my notation for it. So take an n and send it to f sub n. Okay, now I need to figure out what f sub n is. How do you define a function? Well, you give perhaps the formula for it. Let's just use polynomials. That's a sequence, of course, or monomials. So f sub n of x equals x to the n. Now this is a sequence of functions. Okay. When n is 0, x to the 0, well, that's just the constant function 1. So this is the shape you see at time 0. At time 1, I have f sub 1 equals x to the 1, which is just x. So this diagonal. So that's time 1. At time 2, I have, well, what do you call it? Parabola. That's 2. And then cubic and so on. Okay. Now you should imagine as I increase n, you sort of like have this shape, and it sort of starts to bulge this way, right? So, okay. And ultimately, it seems like the limit is sort of like this shape. Of course, that's not a function, and we're going to have to spend some time to make sense of all this. What does it even mean for a sequence of functions to converge to some other function? And we're going to see there are a couple different notions for something like that. But we're going to get to that later. Any questions about this example? Okay. And of course, you can take a sequence of relations if you want it. I'm going to do something slightly more complicated, perhaps. I'm going to take a sequence of subsets. That's also something that is important. Okay. Okay, did everyone sign the attendance sheet? Oh, okay. Thank you. So for instance, sequences of subsets. Oop. That's the other way around. So for instance, one example is this. Now again, to be evocative, I'm going to call it capital A. Capital A sub bullet is going to go from, let's say, well, positive integers to subsets of the reals, so the power set of R. Well, let me define A sub n, nth term, to be, well, the closed interval from minus n to positive n. That I can do. That's a sequence of, well, intervals, if you really want, if you want to call it that. Right? So that's 0. And then here is A sub 1, the first term, and then A sub 2 is from minus to plus 2. And then A sub 3 is minus 3 to plus 3, and so on. Okay? It keeps growing and growing. Any questions about this? Here's another example. Let's call it B sub bullet. Let's say, again, I start with positives. So I start at 1. I'm going to take integers, and I'm going to scale it by, let's say, 1 over n. So B sub n equals 1 over n times integers. This just means this is a set of 1 over n multiples of any integer. So m over n, m arbitrary. So in a sense, this is basically integers, except that I keep the separation between two integers, so to speak, smaller and smaller, right? As n goes to infinity, which we're going to make sense of later. So we first start with 0, 1, 2, 3, and then I look at 0, 1 half, 1, and so on. So somehow I take the whole integers and I keep sort of like pushing them closer and closer as n goes to infinity. Okay, that's going to be an important thing to think about. Now, any questions about any of this? Yes?
So I now understood the difference between the sequence of numbers and the sequence of functions.
The only difference is where this output is. So if your sequence, which is supposed to be a function, right? If it takes real values, that's a sequence of numbers. If it takes, as a function, functions, this is a set after all, I can do that. Now it's a sequence of functions. Okay? Any other questions? Now, here's a warning. Okay, this is an important aspect. A sequence is a dynamical object, let's say. In other words, it's a function. Okay? It's a function that depends on time. If you want, this is the independent variable. You have an independent variable. So don't mistake the function with its image. So if you're doing stochastic processes, for instance, or Brownian motion or whatever, Brownian motion is one thing. Its trail is something else. Okay? There's a subtlety there. So I want to give more examples about this. So, let's say warning. Warning, a sequence is a temporal object. The values it takes is a, well, it's not a temporal object. It's a static object. Is a for some reason this makes noise, like just this one. The other ones, they're fine. While the values it takes is a static object. So the sequence is the function. The values it takes is the image of the function. Okay, yes?
When you say the values it takes, do you mean the inputs or?
Outputs. Yes. So it's a function. So these are the, so this you can call the trail, or using the more formal language, image. Okay. So here's the example. This is the example, or let's give two examples actually. One example is I can take a constant function. In a sense, this you can imagine to be a constant signal. Time still moves, but somehow you're measuring the same thing. This is not, this is different from the image, which is just the number 1. Okay? Now this doesn't have any information about time. It just says, this just gives you that I'm always measuring 1 somehow. Okay? So here's another example. I can think of what is called the alternating series sequence. So I can alternate my signal between plus 1 and -1. Okay? This will be real. So how can I write this? Well, x sub n equals -1 to the n. Right? So if n is even, my sequence gives the value 1. If it's odd, it gives me the value -1. So the image consists of only 2 numbers, +1 or -1. But the motion that the sequence models is an alternating motion. That's the difference. I know this doesn't seem that complicated right now, but as sort of things start to build up and up on top of each other, this is going to be an important point. Always keep this in mind. And of course, perhaps we should think about how to visualize sequences. And probably in problem set 3, there's going to be at least one problem about visualizing some of the theorems that you see in the textbook. It's a function. Any sequence is a function, which means that I can draw its graph. Of course, if you're doing physics or something like that, that is what is called a space-time diagram. But so this is the n variable, and this is the x sub n, and then this is supposed to alternate between +1 and -1. Right? There are multiple ways of visualizing sequences, and as time goes by, I might discuss more things. So let's say we started at 0. At 0, this is 1, and then it's like this. Keeps going on like this. And of course, what is the trail? It's just +1 and -1. In the trail, when you collapse the time dimension, in a sense, you just see these 2 points. Okay? So for instance, perhaps let's look at this. let me define another sequence, okay, with the same trail, but it's going to be a different sequence. So let me continue. Just going to erase this. Again, a sequence of numbers. Let's say x sub n is 1 if n is at most 10, let's say, or 3. And minus 1 otherwise. Okay. Now this is a different sequence. Well, maybe I should call it y sub n actually. It's a different thing. This is a different sequence than this, but their trails are the same. Okay. This models a different motion. It models a different behavior compared to this. So. What did we say? So until time 3, I'm at 1. So 0, 1, 2, 3, and then I stay at minus 1. This is my y bullet sequence, but the trail is the same. Okay? Always keep this in mind. So probably on Friday, when we start talking about something called the limsup of a sequence, that's really about capturing this difference. Because we want to sort of like, I told you that we were going to take sort of tails running off to infinity. And we're doing that on top of just looking at the sup or inf, because we really want to get this asymptotic behavior of the sequence, not just the shape of its trail. Okay, that's going to be a very important point. Any questions about any of this? Okay, so now I'd like to discuss this new object, which is called a metric space. Of course, reals is going to be a metric space, but we need to define it. So a metric space is nothing but a set together with some structure called a metric or a distance function that allows you to, well, tell the distance between 2 points. Now, almost all of you, I think, are going to take the SQL class. There, I think they spend more time on metric spaces. I'm not going to spend too much time on this abstract setting of metric spaces, but at the very least, when it comes to convergence of sequences, I would like to define it in the context of metric spaces. Okay. Let X be a set. A function, okay, let me call it perhaps delta, from x times x, Cartesian product, to reals, is set to satisfy the triangular inequality. Okay, this is one of the cornerstones of analysis as well as geometry, everything. It turns out that, and this is sort of like an insight that has been developed this last century, that once you have a metric, pretty much you're good to go and you can do pretty much anything you want. It's set to satisfy the triangular equality if for any 3 points, x, y, and z, in x, delta of x comma z is dominated by, well, delta of x comma y plus delta of y comma z. And why is this called the triangular inequality? Because, or maybe I should ask you, any guesses as to why this is called the triangular inequality?
It represents the lengths of the side of the triangle.
That's the point, right? Exactly. So if you were to look at the plane, and if you were to take 3 points, x, y, and z, and look at the triangle like this, well, from Euclidean geometry, there's this idea that the sum of this length and this length must be greater than or equal to this length. How many of you have seen this? Okay, some of you. So this delta of x comma z is supposed to model or abstract out this notion of a distance between the two things. Okay. In a second, I'm going to give an example for this. But let's finish this definition of a metric space. A metric is a certain function that in particular satisfies this triangular inequality. I separated out this property because the other properties are sort of technical properties really, but this is a thing that really gives you geometry, okay? Even in the abstract setting, you can start talking about triangles in a consistent manner. So let's continue. A metric or distance function on x is by definition a function is a function. Now I should be a little bit careful because distances are supposed to be non-negative numbers, at least classically speaking. And so let's just focus on deltas like that, but that deltas like this that take non-negative values only. So I'm just going to call it D, really. With satisfying 3 things. First of all, it has to satisfy the triangular inequality. Second, well, what are other axioms? Candidate axioms? Well, certainly, no point should have positive distance from itself. Okay, it's a silly thing to say, but when you're axiomatizing things, you have to say things like this. So, for any x and y in x, the distance between x and y is 0 if and only if x is equal to y. So not only the distance between a point with itself is 0, but in fact, furthermore, given any 2 distinct points, there is a positive distance between them. So somehow you don't allow 2 distinct points to be at the same points. Okay? And then the third one, of course, is that the distance from one point to the other one should not matter in which direction you're measuring. So the distance from x to y should be the same as the distance from y to x. This is called the separation axiom. This is called the symmetry axiom. Separation. Symmetry. Okay, so what is the first example? The first example should be that, well, somehow the real line should be a metric space in a sense. Okay, and so here's our theorem. It's not very advanced of an argument, but because it is so foundational, I'm going to call it a theorem. Well, the function that takes two real numbers and turns out, so outputs the distance between them. What should be the distance? Well, I can just take their difference and then take the absolute value. That would be the distance between them. That indeed satisfies these axioms. So x comma y sent to, well, x minus y in absolute value is a metric. Okay. So this is what is called the Euclidean metric. When you switch over to multivariable calculus, there's going to be an analogous thing happening. Instead of taking the absolute value, you're going to take, well, the norm. These are going to be vectors in multivariable calculus, and you're going to be taking the norm of them. But it's the same idea. And so the proof, certainly, absolute value function is a function that is never negative. So indeed, it's a function from here to there. That's fine. Triangular inequality. Well, let's do the other two first, perhaps. Well, let's check item 2. Well, well, I know that the absolute value takes the value 0 only when the input is 0, which means that x minus y has to be 0, which means that x has to be equal to y. Okay, this is this. Third, well, of course, it doesn't matter in which order I write these, right? Because I'm going to take the absolute value. Well, x minus y, of course, is the same thing as y minus x. Third one, or rather the first property, triangular inequality, it's still not very complicated, but it takes some work. What I can do is the following. I can realize that given any number x, it is bounded from above by absolute value of itself. Right? Because either it's a positive number, in which case absolute value of x is the same thing as x, or it's a negative number, in which case the absolute value of x is plus it. Right? It's the other side. And likewise, minus the absolute value bounds from below x, and same thing holds for y. This is going to give me something that is equivalent to the triangular inequality in this case, but not exactly the version that I want, so maybe I should be more careful. What I want is this. I want the distance between x and z, which is this guy. I want this to be bounded from above by x minus y in absolute value plus y minus z in absolute value. Okay. Oh, okay. So let's do this. confused. Any guesses as to how to continue? I want to show this. For any three numbers, x, y, and z, I want to show this inequality. Okay, let's see. This is equal to this. Okay. Oh, okay, I think that's fine. So I just injected minus y plus y, and it's an equality now. But then this number, if I were to replace it by its absolute value, is going to increase possibly, and likewise this. So this is bounded from above by x minus y in absolute value plus y minus z in absolute value. Okay. Nice. Okay, I think we're done. Likewise, x minus c equals x minus y plus y minus z. But x minus y is bounded from below by minus its absolute value, and likewise this guy. Okay, we're in the clear. Okay, and of course I can factor out the minus here, write it like this. Okay, what does this tell us? This tells us that this number is bounded from above by this positive or non-negative number, and the same number is bounded from below by the same number with a minus. Okay, this is equivalent to saying that the absolute value of this is dominated by this guy. Okay, so it continues from here. Any questions about this? So this is what is called the Euclidean metric or standard metric. It's a metric. And when people don't tell you relative to which metric they are measuring things, at least for real numbers, they mean this one, okay? Now it turns out that there are many other metrics. So here's an exercise. So for instance, for the purposes of application, even though this is standard, it's perhaps not very nice because it is not a bounded function, right? So sometimes you want your metric to be a bounded function. So what you can do is you can change your metric a little bit. So this is an example of this following exercise. If D is a metric on X, then so is, well, D divided by 1 plus D. So take X comma Y, and to figure out the distance between X and Y relative to this guy, I'm saying, okay, measure it relative to D, and then look at this thing. So maybe I should call it D bar, X comma Y equals this divided by this. That's another metric. Of course, the numerator is always less than or equal to the denominator, which means that this is now a bounded metric. Okay, we just change the bounded. You just change the metric to have bounded values. Any questions about these? Now in physics and geometry and stuff, there's another notion of a metric. It's not exactly this, but they are very related. Okay? For this notion of a metric in physics, you need a couple more things. But we're not going to need that. So I'm not going into it. So now that we have a notion of a distance, we can talk about the notion of a convergence, the notion of a convergent sequence. So I should mention function spaces or function sets to have certain metrics, or spaces of subsets, sets of subsets also have metrics. And in problem set 3, you might sort of encounter some ideas like that, and you might see exercises or problems about showing that this is a metric here and blah, blah, blah. But for now, this is what we need. This is the most standard example. So let x comma d be a metric space. Oh, so a metric space is a set with a metric, of course. Be a metric space. And x bullet into x be a sequence. Let me just write down the definition, and then maybe we can discuss some intuition. I'm going to call x bullet to be convergent if it has a limit. Okay, now I need to formalize that idea. Is convergent if, well, what do I need? I need a target limit, right? If there is, let me call it x infinity, there's a point such that, well, here's the famous or infamous epsilon delta stuff. For any epsilon positive, I don't have a delta here because this is a discrete space. So what I want to say is that after finite time, I'm near x infinity. So the way to say this is this. There's an n integer such that after n, the distance between x sub n and the target is bounded by epsilon. That's the definition. In this case, we write, well, limit as n goes to infinity of x sub n equals x infinity, and so on. So let me just write it. You can write it like this, or you can just write x bullet arrow x infinity as sort of like an abbreviation. That's also very common. And x infinity is called the limit of x bullets. So let me write that as well. Now, we had talked about how you should be careful about definite and indefinite articles. When I'm saying it like this, it sounds like this x infinity, the limit, is unique. And that is indeed true, and that's going to be an exercise. If a sequence converges, it converges to a unique limit. Now, what does that mean, or how would you prove this? You would take a sequence and you would say, let's say that it converges to x infinity and then x infinity prime. And then you do something and you realize that x infinity really is the same thing as x infinity prime. Okay. Any questions about this? Now, let me give you some heuristic as to why you define convergence this way. Draw some pictures, and then we're going to keep working on this on Friday. Now, I'm just going to draw the trail, okay? Not the space-time, but just the values. Now, a sequence, so the values of a sequence could be numbers, how many students attend the class on day n, or it could be sort of like a position, in which case it would be a vector and stuff. So let's say that it starts like this. This is x1 and so on. It's going like this. Moves around. Time goes by. In order for me to be able to say that this converges, first I need a target. My target is this, somewhere here. Now, using this epsilon of room principle, what I do is, instead of hitting exactly x infinity, let me try to approximate it using my sequence. So you take a ball, or you take a neighborhood, is what this is called, of all the points not farther than epsilon away from this target. If it is the case that maybe initially this sequence just goes to bizarre places, but eventually if it cannot escape this epsilon ball around the target, and then if you can shrink epsilon arbitrarily small to 0, then you say that this sequence converges to the target. Okay? We're going to talk more about this on Friday, but I think it's a good place to stop. Thank you. Okay, let's start. Good morning. So problem set 2 is due tonight, and problem set 3 is up on Canvas. That's going to be due next week. So problem set 3 is all about sequences and stuff. Now, according to our tentative schedule, I was planning to be done with sequence stuff by today, but I think there is still some stuff that we need to cover, and instead of rushing it, I think I'm going to talk about them on Monday next week, and you're going to see problems about these extra or remaining topics in problem set 4. That's going to be released after midterm 1. So in particular, probably we're not going to be talking about limit inferior and limit superior today, but and there are a couple other things as well. So yeah, let's remind ourselves this notion of convergence, what it means for a sequence to converge. So yesterday, on Wednesday, we had defined this new, more general object, which is called a metric space. A metric space is just a set X together with a notion of distance, D, that has to satisfy certain properties. And I said that whenever you have a metric space, you can talk about, well, sequences in it converging to something. You can talk about convergence in a much more general setting, in fact, as well, but we're not going to need it, so we're not going to go into even more abstract notions of convergence. Okay, so the definition that I gave was the following. I have a sequence, x bullet, and a target, okay, x infinity. And I say that x bullet converges to x infinity if the following happens. So I'm going to rewrite the same thing in a couple different ways, okay? So, so the definition I gave was the following. For any epsilon, positive, epsilon is my error margin. I want to hit my target x infinity using terms in x bullet, but maybe not on the nose, but up to an error of epsilon. Okay? What I'm going to say is that if I can shrink my error margin to 0, that's what I mean by convergence. That's all I need. There is an n, positive, let's say, such that for any lowercase n, after uppercase n, I'm thinking of n as time here. What happens is that the distance between x sub n and x sub infinity is bounded by epsilon. That's the definition. Now here are a couple of different other ways of writing the same thing. Okay, so for any epsilon, so this is another way of reading the same thing. For any epsilon, after finite time, xn is epsilon close to x infinity. So let's write it. That's another way of writing the same thing. Furthermore, using Archimedean principle, whatever, instead of using arbitrary real numbers, sometimes it's nice to just use the reciprocals of integers, so numbers of the form 1 over n. So for any k, I can say positive integer. There is an n such that for any n after uppercase n, the distance between the nth term and the target is bounded by 1 over k. This you can do. Or instead of looking at 1 over k, of course, what you can do is you can look at 1 over 2 to the k. That's also something you're going to see later on why it's important, but I'm just letting you know now. So this is the same thing as this, and then this. For any positive integer, there is an n time such that after this spatial time, the distance between x sub n and the target x sub infinity is bounded by 1 over 2 to the k. Something that decays, okay? This is somewhat more computational because in a sense, if you think about it, this says something about how much time you need to wait to to lose one what do you call it? Order of magnitude, or 1 bit of information here regarding the distance. If you want to shrink the distance between these two guys, this is how much you should wait, it says. Okay. And you can make this more quantifiable and stuff like that. For instance, what you can do is taking the second, or let's say the third characterization, you would fix a k, and then you would look at the set of all uppercase n's, such that the rest happens. Convergence literally tells you that this set, which is a subset of the integers, is nonempty. By the well-ordering principle, it says that there's a least element. That least element is the least amount of time you have to wait to get this bound. Okay? So if you're interested in sort of computational matters, that really becomes important. Okay. Now here's a final way of writing this using sets. That's also very useful. So you can take this statement and turn it into a set theory thing. And so let me write this as well. So for instance, let me use this one. What was the rule? The rule was for alls turn into intersections and their exists turn into unions. So I'm going to take intersection, union, intersection, and then this. So the target is inside k from 1 to infinity n from 1 to infinity, n from n to infinity. You see this running tail. How can I write this? Well, this is a set of all those x's and x, such that x is not farther than 1 over k from the nth term. These are all the same thing. Okay. Questions about any of this? In a second, I'm going to give some examples, but I thought it would be good to talk about this. Logical matters. If you want, these are all exercises to verify that these are equivalent. So, how about the statement that x bullet does not converge to x infinity? So what is the negation of this? Let's also mention that. Well, I'm just going to use one of these statements. So let's write it out. So this is, so you write the positive statement, and then you put a negation in front of it. So for any epsilon, there is an n, such that for any n after capital N, the distance between x sub n and x sub infinity is bounded by epsilon. So this was a positive statement. Now you turn it into a negative statement. Now the rule turns out to be the following, okay? The order of quantifiers here matter, okay? You cannot just take this n here, because when you're writing this out, what you're really saying is that for any epsilon, there's a capital N that possibly depends on epsilon. It may not, but it likely will. Okay? So for any epsilon, there's a capital N that depends on epsilon, such that lowercase n too depends on uppercase n after all. You see, the order matters. So when you're negating 2, you keep the order of everything. You turn for alls to there exists to for alls, and then finally, this statement you negate. In other words, this turns into the following. There is an epsilon such that, or for any capital N, there is an n after capital N such that the negation of this. What is the negation of xn? So what is the negation of the distance between xn and x infinity being bounded by epsilon? Well, you want to say that this is this dominates epsilon, right? Instead of saying that xn stays epsilon close, you say xn stays away from x infinity. Okay, so for some epsilon, you can choose these sample times such that your terms stay away from the target. Okay. Now, perhaps toward the end of today, we're going to talk about something called a subsequence of a sequence. And you can, using that terminology, you can also say it like this. For any capital N, there's a lowercase n, so instead of writing it like this, you say, there's an epsilon, such that some subsequence of x bullet is farther than epsilon, farther than epsilon from the target. So there is a subsequence. Let me just denote it by, well, x prime bullet. Such that for any n, x prime sub n, comma x infinity in distance is bounded from below by epsilon. Now we're going to talk about what exactly this is later today. Okay, I'll define this later today. Okay. Now there's a third statement, which is, or third and fourth statements. X bullet is a convergent sequence, and X bullet is not a convergent sequence. Okay. When you have the statement that X bullet converges, or rather X bullet is a convergent sequence, they don't fix this guy. In which case, so if you wanted to adapt it, well, maybe before going into that, are there any questions about these two? Yes.
So x and are elements of x bullet?
They are values.
Right.
So x bullet is supposed to be a function whose inputs are integers. At time n, x sub n is the value that the sequence gets.
Right.
Yeah. Value, or it could be the position. So your sequence could be sort of like a stock, right? It could be the position of the bunny that you're sort of keeping track of, whatever, in a discretized manner. Any other questions? Okay, so let's look at this. Now I'm going to erase the target. Converges. Now I'm going to delete all this as well. And how do you talk about this statement? Well, now it's included in the definition for a sequence to converge that it has a limit. But this statement, logically speaking, doesn't specify it. Okay? So, and that's why the way I defined it yesterday on Wednesday was this. X bullet converges if everything like this, but in front of it, there's an x infinity. Comma, blah, blah, blah. Okay? And then if I were to look at x bullet does not converge or fails to converge, in other words, x bullet is divergent or it diverges, well, I need to negate this statement. Fails to converge, this is the same thing as x bullet is divergent. If and only if, well, again, I'm going to take the positive statement and put a negation in front of it. So this was a positive statement. There's an x infinity, there's a target such that blah, blah, blah happens, and then turn it into a negation. But you see now, this turns into, for any x infinity in x, there's an epsilon, blah, blah, blah. That's how you do it. And how are you supposed to think about it? Well, given any target or potential target, there is a margin, error margin, that actually some of my terms are able to escape. Okay? So this is all logical stuff, but it's very useful. Any questions about any of this? Let's now look at examples. I'm going to do 2 examples. Example. Again, I'm going to specialize the sequences of real numbers with the standard metric, which was defined like this, right? You take 2 numbers, you look at their difference, and then you take the absolute value so that you have a notion of distance. So let's look at this. In R, recall that I was doing this abuse of notation. This just means that I have a sequence taking real values. Nth term is 1 over n. Okay. Now, as n goes to infinity, this should decay to 0, right, from calculus and stuff. But let's try to formalize this idea. How to do this? So claim this sequence converges to 0. In other words, for any epsilon, there's an n such that for any lowercase n after uppercase n, x sub n minus 0 in absolute value is bounded by epsilon. And this is just like a faster way of writing all these sets and stuff. This is rather common. Sometimes it is useful to be specific about these kind of things, but okay. So plugging everything in, of course, I don't need to write it like this because 1 over n I know is a positive number, so I don't need to think about absolute values. I don't need to subtract the 0 and all that stuff. And of course, when you're writing proofs too, you don't need to write all this. I'm just writing it because this is the first limit that we're taking officially. Such that 1 over n is bounded by epsilon. This is what I want. Okay, I want this. Okay, if I were to take an arbitrary epsilon, positive, well, one of these 4 principles tells me that there is a number like this, less than it. What was it? The Archimedean principle. There's an n such that 1 over n is bounded by epsilon. Now the question is, so far you see I took an arbitrary epsilon, I found a capital N, but how do I handle this part? How do I say that after this capital N2, the same bound holds? Well, what we can say is that for any p, positive number, or non-negative number, let's say, integer, well, n is bounded by n plus p. Taking things to the other side, well, 1 over n plus p is bounded by 1 over n. In other words, because my capital N is such that 1 over n is bounded by epsilon, the same is going to be true for any time after this capital N also. Okay? This is the definition for this sequence to converge to 0. That's literally the definition. Yes.
Sorry, I misread it.
Yes.
Can you explain the third line again?
This one?
Yeah.
Well, so, okay. So this is how we handle these types of statements, right? When you have a statement that starts with for any this, blah, 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 you fix an arbitrary such thing, and then you make sure that you're not using anything specific about that specific choice that you made. In this argument, I'm not using anything specific about epsilon. Of course, this choice of n depends on epsilon, but for any epsilon, there's an n by the Archimedean property. So that's why instead of saying for any epsilon, I turn it into let. I'm just taking an arbitrary epsilon. Archimedean principle literally tells me that for some integer, 1 over n is between 0 and epsilon. So Archimedean, this is by hypothesis, there's an assumption basically. Does this sort of make sense? And then, is this line okay? Okay. Now, if you want to be more explicit about how you do this, instead of assuming something, you would say, let's say that you're from a more computational point of view, you have an epsilon, it's a number, okay, it has a decimal expansion. It could be a rational number, it could fail to be a rational number, but in any event, you can concatenate the decimal expansion of epsilon at some point, and that's going to be a rational number, and then figuring out this number becomes sort of like an algorithm. But you see, math is not as rigorous, let's say, as computer science. So somehow, the way you do math is you have sort of like a computer that has infinite power, can go and run algorithms until the end of time, and then bring back to you the answer and stuff. So we don't need to worry about those kind of things. There's a version of this class where you are supposed to worry about the sort of like steps and how much the computational cost of every step is, but let's not get to that. Already this is too complicated, or it's going to get too complicated. Okay? It is what is called constructive analysis.
Cool.
Yeah. Any other questions? Okay, let's look at another example. Minus 1 to the n. So this was a sequence that decays to 0. Now we look at the sequence that oscillates, that alternates. In other words, my sequence is this. Minus 1 to the n. And if I wanted, I could have written it like this too, right? So I could have said x sub n equals 1 if n is even, if my time is even, and it is minus 1 if my time is odd. This is just a compact way of writing the same thing. So 1 minus 1 if n even, if n odd. What do you think? Is this convergent or not? It keeps oscillating, right? So it doesn't stabilize after finite time. It doesn't matter how long you wait, right? You're going to start letting this act out, whatever it's trying to do. But it doesn't matter how long you wait. It's going to keep oscillating to infinity. So the claim is that this is not convergent. is divergent. Okay, now how to argue? Well, let's think about this. Here's my sequence. And this direction is positive time. And I'm saying that this sequence doesn't stabilize. So let's say that we started at 0, so that it oscillates like so. And so on. Well, let's say that it does converge to something. For a contradiction, say it is convergent. Otherwise, so there's a target, there's a limit, x infinity, in reals, such that x bullet converges to x infinity. Writing down the definition, it says that for any epsilon, there's an n, blah, blah, blah. Let's write it out. Okay. Now you can read it. We can read the statement as, oh, this nth term is epsilon close to x infinity. But you can read it the other way around too. This is a silly thing to do, but the limit also approximates the sequence in a sense. You can say that x infinity is epsilon close to xn. Well, I want to use something like this. I know that the terms of xn alternate between +1 or -1. So let's say epsilon is sufficiently small. Let's say 1/4. If for all epsilon this is supposed to happen, for epsilon equals 1/4, 2, it must happen. So I get to choose specific things. So there's an n such that for any n after n, x sub n minus x sub infinity is bounded by 1/4. And I keep writing the same thing, the same logical statement by just substituting stuff. And I would recommend that you do this initially as well. But of course, as time goes by, you stop sort of writing the same thing over and over again. Okay, now what does this mean? Opening this up, this says that, well, x infinity is in, well, x sub n plus minus 1/4. So let me just rewrite it like that. Open. I just opened up the notion of absolute value. So you see, if you look at, for instance, stock prices and stuff like that, typically there's an average, and then there's sort of like a candle is what they would say. And so I want to think of vertical candles. And so let's say that this is my nth term, okay? And I'm taking this guy. This is plus 1/4 minus 1/4. So the height here was 1. So this is 1 plus 1/4, which is 5/4, blah, blah, blah. I'm saying that there is some n such that after this uppercase n, this special time, my target is both in this interval, in other words, in this interval, if you want to collapse time, but it's also in this interval. Because, you know, after this capital N, it is supposed to be in all of these candles. So what you can do is this. Because you assume that this converges, and because you chose your epsilon to be 1 over 4, you know that there's an n. Take that capital N, okay? X sub infinity is inside x sub capital N minus 1 over 4, and then x sub capital N plus 1 over 4, open. But also, the same thing, same statement, is supposed to hold for lowercase n equals uppercase n plus 1, because n plus 1 is a number larger than this. It's a later time, so it's in the intersection. Okay, now I don't know the parity of this number. Either it is even or it is odd. But what I do know is that exactly one of these numbers is odd and the other one is even. In particular, one of this is plus 1, the other one is minus 1. Either this is plus 1, this is minus 1, or vice versa. In other words, this intersection is empty. That's the reason I chose epsilon to be the small number, which is a contradiction. Because empty set has no element in it. This is a very bizarre way of justifying something rather obvious, but as things sort of start getting more and more complicated, this is going to be all you have, these types of arguments. And whether or not something converges possibly is not going to be as straightforward to see. Any questions about this?
So for that problem, did you just leave off like what set epsilon is a part of and big N?
Exactly. Yeah. I was just.
Write it for a problem.
Yeah. I mean, yeah. It doesn't matter. Yeah. Yeah. I mean, my style. I mean, I told you about the proper way of doing things, but obviously this is not the class for those kind of things, as far as I'm concerned. We have more important things to be worried about. So, some people are worried about those kind of formal issues, but our main issue is calculus. Ultimately, we would like to be able to take a function, differentiate it, set it equal to 0 to find the important points, right? Critical values, whatever. Any other questions? Nice. Yes?
Does that contradiction symbol act the same as the square? It's just saying that you proved it by contradiction.
Exactly. Yeah, I could have said it's a contradiction. I was just lazy.
Right.
Yeah, other symbols that I've seen is some people do this. Some people do this. There's a bunch of different symbols like this. And of course, there's a difference between the way you sort of do math in class, the way you do math as you're talking to other people, and the way you would write math as well. So now you're going to see, for instance, if you had a look at the selected solutions, like the way I write things, my written math language is rather different than my spoken math language. And it's similar to English, of course, or any other language. Any other questions? Okay. Now we have a bunch of things, and we have about 10 minutes. Okay. Subsequences. You're going to need that for problem set 3, so we might as well discuss it. Now, I told you that you should think about sequences as temporal objects, okay? They depend on time. One way to think about a sequence like this, or visualize it, is to think of it as a strip of film, okay? So this is sort of the ticker tape notation. Tape notation, representation. For sequences. So you just list it out. I like to sort of put it in a strip. So this, and then I have the time 0, let's say, and then time 1, and then time 2, and so on. And why is this called ticker tape? Because back in the day when stocks were more analog, you would have one strip of paper for each stock, and you would see the prices, okay? And then there was a machine that would just spit it out. It was just feed it, and then you sort of like see, oh, this is the price, and then oh, the price changed, and so on. Okay? Now we don't use it anymore, but if you go to whatever stocks something, you're going to see that there's like a band. It's like a representative of that idea. In any event, I can also think of this as a movie. Okay, this is my movie. Frame after frame, things happen. The notion of a subsequence is the notion of, it's similar to the notion of editing. Okay, you edit, but you don't change the time. What you can do is you can leave out certain frames, but the order has to stay the same. So that's my sequence. Here's my subsequence. My subsequence itself has its 0th frame, and then the first frame, and so on. But they are not necessarily the same frames that I see before. So maybe the first two were bloopers, so I get rid of them. And the first term, or the 0th term of my subsequence, is the second term of the original sequence. And then maybe let's say that something happened and I don't like this, this frame also. And then I go for x4 and then x5 and so on. Then you keep going like this. This is the idea of a subsequence. In a second, I'm going to define it formally, but it is somewhat scary, perhaps. At least it is scary for me, so I'm just trying to prepare you. And so the way I'm going to denote this is I'm going to just say this. Okay. Now, this doesn't mean that the nth term of this guy is less than or equal to as numbers than the nth term of this guy. I'm saying that this is a sub thing of this thing. Okay. So this is left one is smaller than the right one as a number. This is left one is smaller than the right one as a set, blah, blah, blah. It's the same idea. It's a sub-object, if you want. So I take my sequence and I sample certain times. I don't mix up the times. Time still goes to the same infinity. And there are no sort of like time loops or whatever. It goes to the future. But maybe I'm cutting certain pieces out. Okay? Any questions about this? Yes?
Would it be wrong to say that it is a subset of X bullet?
Well, I mean, you could say that because ultimately sequences are functions and functions are ultimately sets. But when you're writing code, probably it's not very descriptive to say, I'm just adding ones and zeros together, right? Yes?
This seems like a bad notation. I feel like we should have a new symbol.
fair enough. I mean, so the standard way of doing this is like this, okay? If this is your sequence, x sub n, maybe like this, then your subsequence is x sub n sub k. So you use an index for the index. And then for the third subsequence, you take an index of the index of the index. Because I don't like that index of the index of the index, I like to use this, okay?
This is better, I guess.
Well, I mean, after problem set 3, you're going to have your own notation as well, I think.
Yeah, probably.
Yes.
I might also just be lazy enough to continue writing the symbol, because I've been writing that symbol since, like, what, 5th grade?
Yeah.
Since I first learned about equality.
Yeah. Yeah, so in the textbook, this is what they use. X sub n sub k. But then it becomes cumbersome. Another thing, of course, is that I don't want to call my time parameter something. It's a dummy variable after all. So I just want to not think about the name of the time parameter. And so bullet notation allows me to do this. Okay. Now, here's the formal definition. What I need to formalize is this idea of selecting, sampling the times in an increasing manner. Well, I can just look at, well, strictly increasing functions from the time set to itself, okay? Let's be specific. Let's say that I start my time at time 0. A subsequence of x bullets is a sequence, let's call it x bullet prime perhaps. Prime doesn't say anything about differentiability. I'm just using prime as some other thing. Such that for some strictly increasing function from non-negative integers to itself, function, let's denote it by, well, j. I have that the nth term of the subsequence is the j of nth term of the original sequence. And if you want to use diagrams and stuff, you can just think of it like this. I have my original sequence. Its time parameter is like that, taking values in x. X sub bullet prime is yet another sequence. But it is really equal to this up to this time change, so to speak. If you're thinking of sequences as functions, you can think of x prime as this guy composed with this. So it's this is this composed with the j function. Okay. We're out of time, so that's going to be the end of this week's classes. On Monday, we're going to continue on sequences. We have certain theorems to prove, but that's it for today. Thank you. Have a nice weekend.